Welcome to this introduction to the field of signal processing. Signal processing is a widely used technology that pervades every aspect of our lives, and yet few people are really aware of it's even there. It's somewhat of a stealth technology. So what we're going to do today is look at some very basic questions that drive this field, like what is a signal? What is actually signal processing referring to, and what does that mean? What philosophy drives the field of signal processing, and how does it work behind the scenes, and what language is used when we talk about signal processing. To begin, a signal describes how some physical quantity varies over time or space. For example, in this graph, we're depicting the temperature of a river over the course of several days, and you can see that the temperature of the river rises and falls each day with most likely the ambient sunlight and the temperature, the air temperature surrounding it. Now, on the other hand, if we look at an image, we have a signal that varies with respect to space, because at each coordinate in the image, there's a color that reflects the frequency of the light or its color, the frequency or color of the light at that coordinate. So that image, the color changes as we change position within the image. Now, there are many examples of signals, and too many to list, but just to give you an idea, the sound pressure that you're receiving at your eardrums right now due to my voice is certainly a signal. The sound pressure is a function of time. We could consider a radio transmitter or a television transmitter broadcasting a program and look at the electromagnetic wave that leaves the antenna, and that's also a signal. A movie is a signal that varies in both space and time, since the color varies within each frame depending on the spatial location of the pixel, and then over time each pixel also is changing its color. There's the electrical activity of the heart, or the electrocardiogram, that shows how the heart muscle is behaving. We could count the number of sunspots that occur in any month and keep track of that over the course of years, and that would be a signal. Or even the position of your accelerator in your car can be regarded as a signal. So signal processing involves manipulating a signal to change the basic characteristics of the signal or to extract some information from it. So this is usually done, these manipulations are usually done by either a computer or a special purpose integrated circuit or an analog electrical circuit. Now, the computer and the special purpose integrated circuits typically are going to be programmable, and in that sense they have an advantage because they can be adapted to different scenarios and situations. Now, the applications for signal processing are almost as diverse as the number of signals there are themselves, and it's used in almost everyday area of our lives. So you look at the consumer electronics field, things like cell phones use a lot of signal processing. Transportation systems like global positioning devices and airplane tracking also use lots of signal processing. In the medical field, signal processing plays an important role in imaging as well as monitoring things like the electrical activity of the brain or the electrical activity of the heart. The military was one of the first developers and adopters of signal processing, particularly around the use of radar systems for detecting aircraft or missiles. And then remote sensing is another area. For example, astronomy. There's a lot of signal processing that's involved in both producing images as well as interpreting them. And the list could go on and on. There are three different classes of typical signal processing problems. The first one that we'll talk about is the problem of eliminating noise. And in this figure here, we've got a graph of what I'm calling a noisy electrocardiogram. And I say it's noisy because as you look at this waveform, you see there's lots of discontinuous behavior. The signal seems to jump up and down quite a lot and back and forth. And we know from the biology that the electrical activity of the heart should behave in somewhat of a smooth fashion. So these rapid jumps that we're seeing are likely noise that crept into the measurement someplace. So the goal of signal processing would be to eliminate or reduce this noise and produce a clean signal that reflects the true underlying activity of the heart muscle. Now, second problem involves correcting distortion. And in this example, we have a blurry image. So the blur is the distortion. And what I'd like to do is take this blurry image and perhaps some knowledge of the nature of the blur and run it through a signal processing algorithm that would reconstruct the sharp, focused image that's behind this. Now, this sort of distortion correction is very obvious with images, but it also applies to signals that get distorted in time, such as when you talk on the telephone, and there's a need for correcting the distortion that gets introduced along the way. A third signal processing problem is is a little more abstract and involves extracting some piece of information that's embedded within the measured signals. And the best way to clarify this is with an example. So let's suppose we want to use a radar system to determine the aircraft position and velocity. Well, the way the radar works is it first transmits an electromagnetic pulse that then travels through the air and it hits the aircraft and is reflected back, and then the radar system measures what's reflected back. Now, that reflected signal in itself is not all that interesting, but the information that it contains is what we're after. Because the position, or at least in this simple example, the distance of the airplane, is governed by the time delay that it took for that pulse to travel from the radar to the airplane and back. Knowing the speed of light, we can figure out how far away it was once we know the time delay. Secondly, the relative velocity of the airplane with respect to the radar is embedded in the Doppler shift that we would see in the pulse. So if we can extract a Doppler shift from the measured signal, we can determine the velocity, the relative velocity anyway. So in these cases, the information that we're interested in is embedded within the signal, and we have to extract that from what we measure. Now, the philosophy of signal processing is driven by the use of models. Models play an absolutely fundamental role. So when we're trying to distinguish signal from noise, differentiate those things and separate them, that's done using a model for what we think the signal is and what we think the noise is. So when I just described the electrocardiogram, I said that the electrical activity of the heart should be varying in a smooth manner with respect to time. So that's a model. Or when we took the image and cleaned it up to remove the distortion due to blurring, we use a model for the blur to do that. And similarly, this last example, where we use the time delay and the Doppler shift embedded in the data to estimate the aircraft's distance and relative velocity, again, we have a model driven in that case by physics, the Doppler and propagation time of electromagnetic radiation. So models are derived from prior knowledge. We can use the physics or the biology, like in the electrocardiogram case, or any other information we have to help us understand what is our signal and what differentiates our signal from noise or other things in the data. And once we have these models, we then develop processing procedures which exploit the information contained in those models. So that is used to develop an algorithm, if you will, that acts on our data to accomplish the goal. Now, there are several issues with modeling, and one that needs to be kept in mind is that if you choose a poor model, you're going to end up with poor performance. What I mean by a poor model is one that doesn't reflect what you're interested in. So, for example, if the real electrocardiogram is smooth, but you assume that it's the rough part of the signal, then you're not going to get a cleaned up electrocardiogram. You're going to get noise. Now there's a more subtle trade-off that occurs with respect to the complexity of a model versus its performance. Okay, and I've drawn two models represented by equations at the bottom here. On the right, in blue, we have a fairly complicated looking equation that would be a model for, say, a signal y of n. Whereas on the right, in green, we have another much more simpler model for a signal y of n. The more complicated model generally is going to require more computation. And the other aspect is the accuracy. Now you might say, well, a more complicated model certainly could be more accurate, should be more accurate than a simple model. And that's true, although when we look at data that has noise in it, it sometimes doesn't work that way. Because what happens with noise is that if you have a model that captures really subtle variations in the signal, noise is going to mask those. And your model will get confused by the noise. And in those cases, a simpler model often works better than a more complicated model. Now, the language of signal processing involves mathematics. In particular, calculus and linear algebra play important roles, with linear algebra perhaps being more dominant in the field of signal processing. The inner product or dot product is extremely pervasive, okay? And in fact, some of these integrated circuits that are designed to do high-speed signal processing rely on architectures that efficiently compute inner products. Now, probability and statistics also play an important role because we've got noise and we have other uncertainty. When that radar reflection comes back, there's a Doppler shift, but we don't know what the Doppler shift is. In fact, we want to figure that out. So there's uncertainty about that. And probability is a way of modeling uncertainty. Statistics also provide a way for us to characterize how confident we are about the answers we get back or the results of our signal processing. In conclusion, we've seen that signals and signal processing pervade every aspect of our lives. Signal processing is often used to address three different problems. One is to reduce noise in measured signals. Another is to correct distortion. And yet a third would be to extract some piece of information from a signal. To do this, we rely on mathematical models, and it is the language of mathematics that is used to describe the field of signal processing.